So today, we're going to talk about one of the most incredible ideas in all of physics. The idea that mass literally tells spacetime how to curve, and that curve, in turn, tells mass how to move. It's a cosmic dance, and we're about to dive right in.
For the longest time, everyone just assumed space was, well, just empty space, a static, boring backdrop for all the action in the universe. But in 1915, Einstein came along and completely flipped that on its head. He said that space and time are actually woven together into this four-dimensional fabric he called spacetime. And here's the kicker. This fabric isn't just sitting there. It's an active player that can bend, warp, and even rip.
I mean, what a mind-bending idea, right? But a beautiful theory isn't enough. You gotta have proof. So the big challenge was, how do you even begin to test something that rewrites the fundamental rules of the universe? And what kind of weird new things might be hiding inside those complicated equations of his?
And this is where the story gets really wild. The first major breakthrough didn't happen in some quiet mountaintop observatory. Nope, it came from the trenches of World War I. A German physicist named Karl Schwarzschild, of all things, was serving as an artillery officer when he became the very first person to crack the code and unlock the theory's predictions.
So that brings us to our first section. Think of Einstein's equations like a master lock on a cosmic safe. Finding a solution is like figuring out the combination. It opens the door and reveals the secrets of how gravity works in a very specific situation. And Schwarzschild, well, he was about to find the very first key.
Okay, so here's the key thing to remember. When you're tackling a problem this huge, you don't start with the most complicated thing you can imagine. You start simple. So Schwarzschild decided to solve the equations for the most basic object possible. A single, perfect sphere of mass, not spinning, just sitting there all alone in space. Like our sun, for instance.
And this is what he came up with. The Schwarzschild metric. Now don't let all the math scare you, that's not the point. The important thing is what this is. This is the very first exact solution to Einstein's equations of general relativity. Ever. It's like a perfect recipe that describes exactly how space-time curves around a simple mass. This one equation, this one key, unlocked everything that came next.
So, we've got the key. What's the first secret it unlocked? Well, it turned out to be something really strange about the way planets orbit their stars. It turns out Newton's picture of the solar system, it wasn't quite the full story.
This slide lays it out perfectly. On the left, you've got the old-school Newtonian view. Gravity is a simple force, a pull, and planets trace out the exact same perfect ellipse over and over again, forever. But then you look at Einstein's universe on the right. Because the planet is moving through space-time that's been warped by the star, the orbit doesn't quite close back on itself. The whole ellipse actually rotates, very slowly, over time.
So what's causing this difference? It all boils down to a tiny but absolutely crucial correction in the math. This chart basically shows gravity's pull at different distances. That dotted line, that's Newton's theory. The solid line, that's Einstein. See how they're almost identical? But look way over on the left when you get really close to the star. Einstein's theory predicts a slightly stronger gravitational pull, and that little extra tug is what makes the whole orbit wobble.
And wow, this shows you exactly what's happening. On the left, you've got that clean, predictable Newtonian orbit. But on the right, that's the real deal, the Einsteinian version. Every time the planet makes a loop, its closest point to the star shifts forward just a tiny bit. Over a long time, it traces out this beautiful spirograph-like flower pattern. And that wobble has a name. It's called precession.
And here is where it all just clicks into place. For decades, astronomers had been tearing their hair out over Mercury's orbit. They could see it wobbling, precessing, by a tiny amount that Newton's laws just could not account for. It was a huge mystery. But when they plugged the numbers into Schwarzschild's solution, the prediction matched the observation perfectly. It was the first stunning, undeniable proof that general relativity was right. Okay, so that was secret number one. But the next secret was, if you can believe it, even wilder. If gravity is just the shape of space-time, then it shouldn't just affect things with mass, like planets. It should affect anything that travels through space-time, even light itself. So Einstein's theory made another shocking prediction. Gravity bends light. And the logic behind it is actually beautiful and simple. Light always takes the straightest possible path. But if space-time itself is curved, say by something massive like our sun, then the straightest possible path isn't a straight line anymore. It's a curve. Light is just following the contours of space.
This picture shows you exactly what we're talking about. A ray of light from a distant star starts out on a straight path,
But as it gets close to the sun, it has to follow that big dip in space-time that the sun's mass creates. So from our point of view, back here on Earth, it looks like the star is actually in a slightly different place in the sky.
And once again, the theory didn't just say light bends. It gave a precise, testable number. It predicted that starlight just grazing the edge of the sun should be deflected by exactly 1.7 arcseconds. Now that is an insanely tiny angle. It's like the width of a human hair seen from 70 feet away. But in 1919, an expedition led by Arthur Eddington measured it during a solar eclipse. And the result? Einstein was right. Again.
All right, get ready for secret number 3, because this one might just be the most mind-bending of them all. Gravity doesn't just bend space, it actually warps the flow of time. According to the theory, the stronger the gravity, the slower time itself ticks by.
So, how in the world do you test that? Well, in the 1960s, a physicist named Erwin Shapiro came up with a genius experiment. The idea was simple. Send a powerful radar signal from Earth, bounce it off a planet like Venus when it's on the other side of the sun, and then time, with incredible precision, how long it takes that echo to come back.
Now you might be thinking, well, of course it takes longer. The path is curved. And that's true. That's part of it. But the theory predicted something way more profound. As that radar signal dips down into the sun's deep gravity well, it's traveling through a region where time itself is literally running slower. And that slowdown adds to the signal's total round-trip time.
And that is exactly what Shapiro measured. The radar echo came back just a tiny fraction of a second later than it should have if space were flat. This Shapiro delay was direct, measurable proof that massive objects don't just curve space, they literally slow down the passage of time.
Okay, so we've got wobbly orbits, bent starlight, and slowed down time. 3 incredible confirmations of the theory. But Schwarzschild's elegant little equation was still hiding one final and truly extreme secret. It predicted a place where the curvature of spacetime becomes so intense that geometry itself seems to just break.
Hidden deep inside the math was this critical boundary, a line in the sand now called the Schwarzschild radius. It basically represents a point of no return. The equation showed that if you could somehow squeeze any object down smaller than this special radius, the curvature of spacetime around it would become infinite. It would literally punch a hole in the universe.
For an object with the same mass as our sun, that radius is just under 3 kilometers. Just let that sink in for a second. The entire mass of the sun, something over 1 million kilometers wide, squished into a space smaller than a small town.
And that leads us to the final haunting question. What happens if you actually do that? What do you get? You get an object that has so completely warped the fabric of space-time that it has torn it apart. An object from which nothing, not even a beam of light, can ever escape. The final, darkest secret hidden in Schwarzschild's solution is the black hole.